Hello everyone, welcome to today's class. Today we are looking at AS Chemistry paper 9701 stroke 13 for May June 2024, and this is part 1 for questions 1 to 10. Question 1. X is an impure sample of a group 2 carbonate, M carbonate. X contains 57% by mass of M carbonate. The impurities in X do not react with hydrochloric acid. 7.4 grams of X is reacted with an excess of dilute hydrochloric acid, and 0.05 moles of group 2 metal chloride is produced. What is the identity of the group 2 metal? Now, first of all, the reaction between this carbonate and HCl, the equation is this one here, HCl. We shall get the salt, which will be M, then chloride. Since it is from group 2, then we shall have a 2 here. Then plus carbon dioxide plus water. Then to balance this equation, I will put a 2 here to balance the chlorine. Not so? Then what else? Hydrogen is 2. No, hydrogen is 2. Oxygen is 3. Oxygen is 3. Carbon 1, M1, M1. Okay. So that is the one there. Now we are having 0.05 moles of the metal chloride. 0.05 moles. Now, when you look at what we are having here using the stoichiometry of this reaction, it is 1 to 1. Okay, 1 mole of the carbonate produces 1 mole of the chloride. You see that? So that means if we have 0.05 moles produced for the chloride, then they come from 0.05 moles of the what? Of the carbonate. You see that? So we are having 0.05 moles of the carbonate. But again, they said 7.4 grams of X is reacted. So how do we find the moles? This is 7.4, then divide by the MR. So we don't know the value of M. Then carbon is 12, and then oxygen, we know that its AR is 16, but there are 3 of them. So this will be 48, then plus the 12, that will be 60, then plus the M. So this is how we get the what? The moles, which is 0.05. But they said that X contains 57% by mass of this. So that means even the moles that are going to be produced are 57%. So that means we have 57% of these moles are the ones that gave us this. You see that? Now we make X the subject of the formula. I mean M the subject of the formula. So we shall have up here 7.4 times, this one is 0.57. Then this one is equal to, this is 0.05 into M plus 60. Then that means our M is going to be equal to this 7.4 times 0.57. Then you divide by the 0.05. Okay, 0.05. Then after we take the 6 to this side and we subtract it from there. So when we put in the calculator, what do we get? 7.4 times 0.57. Then we divide by 0.05. Then we subtract 60. This one gives us 24.36. 24.36. When we check in group 2, this is approximately the AR for magnesium. So this is magnesium. When we come to group 2 here, you can see the AR for magnesium is 24.3. You see that? For calcium, it is 40.1, strontium 87.6. So the answer was that for magnesium, which is A. Then question number 2, which of these samples of gas contains the same number of atoms as 1 gram of hydrogen gas? Now, 1 gram of hydrogen gas appears as a diatomic what? Molecule. That means we shall get 1, then divide by 2 times the AR of hydrogen, which is 1, okay? Then times 6.022 times 10 to power 23, the Avogadro's number. So 1 mole of a substance contains 6.022 times 10 to power 23 particles. They can be ions, they can be atoms, they can be molecules, you see? And then after this one here, since we are looking at atoms, hydrogen has gotten how many atoms? 2. You see that? So I will multiply this one by 2. That means this one will go, and I remain again with this number here. Now, let's come to this one, 22 grams of carbon dioxide. So the MR for carbon dioxide is 44, so we shall have 22 out of 44, then times 6.022 times 10 to power 23. But carbon dioxide has how many atoms here? We have 2 oxygen atoms and then 1 carbon atom. So that means we shall multiply by 3. You see that? Then this other one here will be 8 out of 16 times 6.022 times 10 to power 23. Methane has gotten 5 atoms there. And then this other one is 20 out of 20 times 6.022 times 10 to power 23. Neon is monoatomic. So it is a monoatomic gaseous atom. Then we shall have times 1, okay? And then ozone will be 8, then divide by the 48 times 6.022 times 10 to power 23. But ozone has gotten 3 oxygen atoms. Now, which of these corresponds to this? And we get that value. When we look here, this one goes first of all, and then times 1. So this is the one here. That means our answer has to be C here. Because you can see this is a half of the 5, that is 2.5. But we are looking for a 1, then times the 6.022. The rest do not give us. Okay? So that is that. Question 3. What is the total number of protons, neutrons, and electrons present in an ammonium ion with the relative formula mass of 21? So if the relative formula mass is 21, now we know that an ammonium ion is this one here. Okay, we have the nitrogen. Nitrogen is in group 5, or we can say group 15. So it is in which position? Position 7, nitrogen. Now, that is 1s2, 2s2, 2p6. No, not 2p6. So if it is 7, this will be 2p3. So that means here in the nucleus we have these 2, okay? Then 1, 2, 3, then 4, and then 5. So we get a hydrogen here, a hydrogen here, a hydrogen there. You see? So each here, that is a hydrogen, another hydrogen here, and then that one there. Then another hydrogen ion, this one, remember there is a nucleus which has 1 proton, so the electron which was here got lost. You get it? Then it remains as a proton, positively charged, because you know protons are positively charged, right? Then we are going to have that hydrogen coming here and then shares with this nitrogen. So nitrogen is the one that gives this hydrogen the 2 electrons. So this is dative what? Bonding. Okay. Now, what we are having here, if the MR is 21, of course for hydrogen, it is in position 1. Its AR is also what? 1. Now, if the relative formula mass is 21, there are 4 hydrogens here. So I will say 21 minus the 4. What do we get? We get 17. That means the nitrogen we are having here, its mass number is going to be 17. Okay, and then this is 7 here. You see, so the nitrogen has gotten protons are 7. Okay, then neutrons will be 17 minus 7, that will be 10. And then electrons, nitrogen has how many? Of course, nitrogen in here has 7. No, it has 9. Okay, 9 electrons, because you can see these are 2, then 3. No, actually I made a mistake here. No, it is there. Okay, so these are 2, 3, 4, 5, 6, 7. Okay, it has 7. Pardon me there when I said the 9. So this is 7. Now hydrogen, there are 3 of them. Each of them has 1, 1. Then there is also a hydrogen ion. So hydrogen here has gotten how many electrons? The electrons are 1. So there are 3 of them. So we are seeing 3 electrons. Are we there? Then 3 protons. Each of them has 1 proton. And neutrons, of course, they are not there for a hydrogen atom. Then we have a hydrogen ion. A hydrogen ion has 1 proton, no electron. You see that? So now let's count. We shall say 3 plus the 7. What do we get? 10. Protons, 3 plus the 7. What do we get? No, actually protons are 7 plus 3, 10, then plus 1, 11. You see that? Those are 11. So we look for 11. It is here and then here. Then let's go to electrons. Electrons are 7 plus 3. Those ones are 10. So we look for 10 here and here. We go to neutrons. 10. Neutrons are 10. So it is not here, then it is here. So that means our answer is A. Question 4. This question is about the first Ionization energies of magnesium and neon. Which row is correct? So before we look at those, we need to know the electronic configuration. So we have for neon, it is in position 10. So 1s2, 2s2, 2p6. And then magnesium, it is in position 12. So we have 1s2, 2s2, 2p6, then 3s2. Now, because of this other shell, then that means that the nuclear attraction for the outermost electrons has decreased because of the increased what? Shielding from the inner electrons. Okay, so this simply implies that it will be easier to remove an electron from magnesium compared to this one of neon. Okay, all right, so the first ionization energy here for neon has to be greater than that of magnesium, so it is here and here. Then type of electron removed. So from magnesium, we are removing from the S, okay? And then from neon, we are removing from P here. So that means our answer is D. Question 5. Arsenic forms a compound with fluorine. In this compound, the arsenic atom has no lone pair of electrons and there are no dative bonds. Selenium also forms a compound with fluorine. In this compound, the selenium atom has no lone pair of electrons and there are no dative bonds. In which compounds are there 2 different bond angles? We should assume that 180 degrees bond angles should be ignored. Okay, now let's go and look at the groups from which we can get arsenic and what? Selenium. Okay, when we come to the periodic table, arsenic is here, and selenium, you see group 15, that is where we are seeing arsenic. Then group 16, selenium, that means they have 6 electrons in the outermost. This selenium has 6 electrons in the outermost, just like sulfur and oxygen. And then arsenic will have 5 electrons in the outermost shell, just like phosphorus and nitrogen. Okay, so we have seen that arsenic is in group what? In group 15. And then selenium, arsenic, I think it is AS. So selenium in group 16. So if I have arsenic here and it is in group 15 and it forms no lone pair, because I would have expected something like this, just like in ammonia where we have nitrogen, it has a lone pair, and then the 3 maybe hydrogens here. But they said there are no lone pairs. That means all of these electrons are fronted for bonding. So that means we have 5 of them. And the structure we are going to have is this one here. So you will have a trigonal pyramidal, first of all. Okay. But then we shall have one up here and then one down here. So it's like you have a triangle, then the arsenic is here, then there is one up, and then there is one down. Just like you can be there on the table, and then you have a square for the octahedral. You have a square here. These are the diagonals which bisect each other and meet at 90 degrees. Then there is up here. So you hold something up, and then you also hold something down. Okay, that is the octahedral. So for this one, we are having a triangle here, horizontal, and then we have vertical. We have something here and then something down here. You see that? So that is what we are going to have here. We shall have fluorine. We shall have fluorine down here, then here, here, and here. Of course, since this one is a triangle, just like we have in boron tetrafluoride, okay, these are bond pairs, the 3 bond pairs, the angle has to be 120. So meaning here I'll have 120. It is the same angle between this and this, and also the same angle here. Okay, then since this triangle of ours is horizontal, then we have something vertical here. The angle between the horizontal and the vertical is always 90 degrees. That means whether it is here or there, it is 90 degrees. So we are seeing the 2 angles here are 90 degrees. Then we have 120, but there is also 180 degrees, okay, in between these 2 here. That's 180. But they said we do what? These ones, we should ignore them. So that means the 2 different angles we are seeing here are 90 and 120. Now let's go to we go to selenium. Selenium is in group what? 16. So it has 6 electrons. Okay, it fronts all of them for bonding. So just like I said before, you have a square here. So these ones first go into this square, and they do what? They bisect each other. These diagonals, they're at 90 degrees. So that means the angle we have here is 90, 90, 90, 90. Okay, then after that we can have this one here up, and then this one here down. Okay, so the angle in between, because this one is vertical, this one is horizontal, then this is vertical, so the angle has to be what? 90 degrees. So let me just represent the 90 by 1 here, and then when I put the vertical one here, so that I can easily put this other 90 there. So we are seeing 90 in between these ones that are horizontal, and also we see 90 between these ones that are vertical. So this one which is vertical and the horizontal. You see that? So, and of course we also have these which is 180 degrees. Okay, so because of that, and they say that we should ignore the one of 180. If you look very well, the 2 different bond angles, we see them in arsenic pentafluoride. So that means it happens in arsenic fluoride only, and the answer becomes B. Then question 6, a structure of borazole is shown here, and they are saying which shape is borazole and how many pi electrons are there in the structure. Now, you can see that where there is a B, there is a bond pair here. They put the hydrogen, okay? Then there is this double bond and this single bond. So when you look at this, you look at this one here, even the one for nitrogen, all of these ones are in a plane, the trigonal planar. Trigonal planar. So the fact that there is that word planar, then it is in a plane. So it has to be planar. Are we there? Here and here. Then number of pi electrons. So whenever you see a double bond, then there is sideway overlap of the p orbitals. Okay? But there is also this sigma bond here. For example, if this is the one like that. So those two, that there is head-on overlap, they give us the sigma bond. So we are going to have this sigma bond, okay, maybe between the B and then the nitrogen, then there is a pi bond. And for every pi bond, there is always an electron, then an electron here. So they share the electrons. So meaning in a pi bond has 2 electrons, okay? 2 electrons. So here we have 2 electrons, and then here 2 electrons. Those ones become how many? 6. So that means it will be here, not this one here. And the answer will be this. Now, they put for you 3 here. That one represents the pi bonds. It is 1, 2, and 3, but the pi electrons are 6 because each bond contains 2 electrons. Question 7. The diagram shows the apparatus used to find the relative molecular mass of a volatile liquid. When a 0.10 gram of a volatile liquid is injected into a syringe, all the volatile liquid evaporates and the volume increases by 85 cubic centimeters. Volatility is the tendency to vaporize. So they are saying here that the heater maintains a temperature of 400 K, and that is kelvins, and the experiment is carried out at a pressure of 101300 pascals. If the vapor of the volatile liquid behaves as an ideal gas, which expression can be used to calculate the relative molecular mass of the liquid? So that means what we are supposed to use is the PV, which is equal to nRT, n representing the number of moles, so which is the same as saying mass divided by the mR, and then times the RT. That means when we are to find M, you can MR, you can cross multiply. So your MR is going to be equal to the M, then RT, then we divide by PV. Now, when using this method here, when we are using this expression here, or the equation, we are going to use pressure has to be in pascals or Newton per meter squared. Why Newton per meter squared? Because pressure is equal to force over the area. Area, the square units are meters squared. This one is Newton, right? So Newton per meter squared. Then the volume, because pressure is in Newton per meter squared, then volume has to be in meters cubed. Now, of course, kelvins, temperature has to be in kelvins. Now, we know that here the volume is given in cubic centimeters, so we have to convert it to meters cubed. We know that 100 cubic centimeters are equivalent to 100 centimeters are equivalent to 1 meter. Then how about when we cube both sides? So 100 cubed then centimeters cubed will be equal to 1 cubed then times meters cubed. So meaning 1 centimeter cubed shall be equal to 1 over, this one will be 10 to the power of 6. 10 to power 6, then meters cubed, which is the same as saying 10 power negative 6 meters cubed. That is 1 centimeters cubed. So that means if I'm finding MR, I will say the mass is given as 0.10 here, then times R. Our R is 8.31, the molar gas constant. Then T, the temperature is 400 what? Kelvins. You can see it here. And then out of the pressure was given as 101300, which is here. And then times the volume, which is 85 cubic centimeters. But where there is a cubic centimeter, I'm going to put this. So I will say times 10 to power negative 6. You see that? Now, when we look through our options here, what do you think is the answer? 0.1 times 8.31 times 400 divided by 85 times 10 to the power of 6. I mean negative 6. Then times 101,300. That means our answer has to be C. Question 8. The table shows physical properties of four substances W, X, Y, and Z. What are the identities of W, X, Y, and Z? When we look at W here, the melting point is high, boiling point is high, electrical conductivity of the solid is poor. And then when we look at W here, this is an ionic compound, okay? And it cannot conduct electricity when it is a solid, so that is true. Then electrical conductivity of the liquid is good. When you melt this one here, it becomes a liquid. That means the ions are free to move, so it can conduct the electricity. And then electrical conductivity in water, when you dissolve these ones, they separate into the ions. So the ions are free to move. That means they can conduct electricity, okay? So that means this W here is an ionic solid, right? Ionic solid. And indeed, all of these ones are ionic solids. We go to X. The melting point is negative 109. It is too low. And then the boiling point is at 39. That means at room temperature, which is 25 degrees, we are seeing a liquid. Are we there? Electrical conductivity of the solid is poor. Electrical conductivity of the liquid is poor. And then it is insoluble in water. Now, X here must be a covalent. Covalent. I had written covalent. So this is covalent molecule. Okay, with a simple structure. But let me say covalent simple molecule or simple covalent molecule. Okay, that is the X. So when we look here, covalent, this is ionic. You see, this one, the HCl can easily dissolve in water, and yet they said this one is insoluble in water. Do you see that? So that means it can either be this or that. So this one is off. Then we go to Y. The melting point is 1535. Even here it is 2750. It is high. Electrical conductivity of the solid is good. Electrical conductivity of the liquid is good. That is when it is molten. Okay. Then electrical conductivity in water it is insoluble in water. Okay. It is insoluble in water. So that one here has to be the iron. Okay. When you put this one here, potassium, okay, when you put potassium in water, it reacts with it. It's an explosive reaction, okay, to produce potassium oxide and then the hydrogen. You see that? So it's an explosive reaction, so potassium has to be off. Now, which one has gotten the 3 ticks so far? It is A and C. Let's go to the next one. Now, when we go to this other one here for Z, they are saying the melting point is high, the boiling point is high, electrical conductivity of the solid is poor, and then for the liquid is also poor. Okay. Then what else? By the way, this one, we said it is a metal. Then here, we have electrical conductivity in the liquid. It is insoluble. It has to be this silicon here. Aluminium is off, because when I melt this one here, I'll have the aluminium 3+ ions and then the oxide ions. Okay, these ones will be in position to move about. You see that? And yes, we know that aluminium oxide is insoluble in water. That is why we have the overhead power cables made of aluminium, because it even has a low density. So what happens is that the aluminium will react with the oxygen, then it forms this what layer. So this layer covers that what that wire. So even if it rains or what, it will not react again. So it acts as a layer that protects the aluminium here. You see that? So it is insoluble, yes, but electrical conductivity here, it is good. When you melt this one here, I have the ions here that are free to move, you see. But for silicon, first of all, this one is giant molecular. Okay, giant molecular. So if this one is giant molecular, and this one here is giant ionic, you see. So that means our answer has to be this C here. Z has to be silicon 4 oxide. Question 9. The apparatus used to determine a value for the enthalpy change of combustion of butane 1O is shown. The mass of 1 cubic centimeter of water is 1 gram. Okay. Then here we are given the initial mass of the burner plus butane 1O, which is this one here. And then the final mass of the burner and butane 1O is this one here. So it has decreased by something. So that is the one which was burnt here. So we need to know the mass, okay? The mass of this alcohol that was burnt. So mass of burnt butane 1O. So this one is going to be 58.34 minus 57.85. What do we get here? 58.34 minus 57.85. That is 0.49 grams. Then we also need to get the temperature change, because we see it here. This is 41.1 and then this is 17.6. So change in temperature, we actually call it the T. This one is going to be 41.1, then minus the 17.6. So what do we get? 41.1 minus 17.6. This one gives us 23.5. So 23.5 degrees C. So whether the temperature is given in degrees C or kelvins, we just take the change. So it is 23.5. You don't need to convert the temperature to kelvins, okay? Now, after here, because when you convert this to kelvins, so when you subtract, of course, that 273 you have added on both of them will disappear. You see that? All right. Then next, we need to find the energy change here. So the dH here is going to be equal to mc then dt, or sometimes people say mc theta. The mass here is the one of the solution, or what is being heated. So this is the one here, 175 cubic centimeters, and 1 cubic centimeter is approximately equal to 1 gram. So that means the mass we are having here is 175 grams. And then C is the specific heat capacity of water, which is given on that formula sheet, which is 4.18. Okay, then times, this is 23.5. If we can check that list of formulae or the list of constants, you can actually see it as 4.18. You see, when you come to this list here, specific heat capacity of water, you see it here, 4.18. So when we multiply here, then what do we get altogether? 175 times 4.18. Sometimes people use 4.2, but use the one that is given on your list. Okay, then times 23.5. This one gives us 17190, 17190.25. Now, joules. This energy here, which is released, of course, it has a negative sign because it is an exothermic reaction. This is the one which was released by this mass which was heated. So we shall say that 0.49 grams of butane 1O, okay, released 1719 0.25 joules. How about 1 mole of butane 1O? And 1 mole of a compound weighs its molecular mass, okay, or its RFM, relative formula mass. So this one is a molecule, so we call it relative molecular mass. Then for ionic compounds like sodium chloride, we don't say molecular mass, we say relative formula mass, okay, RFM. So that means 1 mole here weighs what? 74. So if the 0.49 released this, how about the 74? So 74 grams of, oh, by the way, another person can say, I'm going to convert this one to moles. Then they will say, those moles, okay, released this. Then how about 1 mole? It is okay. But even if you just use this mass here, then this mass is for the 1 mole. You still get the same answer. So 74 grams of butane 1O would release, then you get the 74 times 17190.25, and then we divide this one by 0.49. So what do we get when we put the whole of this in a calculator? 74 times 1790.25, then down here we are having 0.49. So that is 2596 on the rest of those figures. So 2596078.571. So when we round off to 3 significant figures they want, that means you round this 6 to a 9 and you add a 1. So that means this one will be 260. But how many are these ones here before the decimal point? There are 4. There's a 6, there's 0, there's 7, and 8. So I need to add on more 4 zeros. 1, 2, 3, 4 joules. Okay. Now, this one here, this is joules per mole. When you look at the answers here, it is supposed to be in kilojoules. So that means we shall have 260, in fact 2600 up to here. So you divide all through by 1000, so the 3 zeros will go. Then I'll have kilojoules per mole. And that means our answer is going to be what? C. Remember here I used the word release. That means the energy which is here has a negative. You get it? Because it is exothermic. Question 10. In the high temperatures of car engines, nitrogen reacts with oxygen to produce nitrogen monoxide. This is the reaction given here, and we consider the enthalpy of reaction is positive. So this is an endothermic reaction. So because it is an endothermic reaction, that means the particles take in energy, and then the products are going to come out with energy that is higher than that of the products. So in our options, based on this energy here, this A has to be off, okay? Because we can see now the products are below the reactants. For this one is an exothermic, that is where energy is released to the surrounding. That means the products remain with little energy. You see that? So A is off. And then when you look at B, B is okay because this one, the reactants are higher than the products. Then we also look at this one here. Even C is okay based on the energy given, and also D is okay. Now let's continue. They are saying this reaction has activation energy. Activation energy is the minimum amount of energy particles must possess in order to react. So which reaction pathway diagram correctly represents this reaction. So you have to look at where the reactants are, this line here, and then the activation energy always starts from there, and the arrow has to be facing up because you have to overcome that energy. So you need to put in energy to overcome that barrier. You see that? So here I'm going to put off this because activation energy doesn't begin from the reactant line. It begins from this one. I mean, doesn't begin from the product line. It has to begin from here. Okay, so this one here is okay. Already this one is off. Okay, already this one is off. I was going to say this one is okay, but it is already off because this one represents an exothermic reaction. You see that? Then when we come to see here, the enthalpy is positive. We can see here that is between the reactants and then the products, and it is positive. The arrow is facing up, so that one is okay. But then here they are putting the arrow down. That is wrong for the activation energy, and also this one is facing down. That means it is an exothermic reaction. That is for the one that faces down, and already this one is even positive, so this one is off. So our answer then has to be this C here.